Welcome for the next session on Module 2. And for today's session, we are going to discuss two cases, which is infinite solid and semi-infinite solids. Now, in this case, sorry. So in this case, why exactly can't we use lump system analysis under which scenario? So everyone is familiar, like at some point in their life, they have maybe if you are a non-vegetarian, if you had uh, roasted or maybe have ate a roasted chicken. Okay, so if you have a roasted chicken, so in that case, if you take a cross section of the chicken, it looks somewhat like this. And you will see, since the oven was exposed to the outer layer, so outer layer will be uh, much more burned and heated. So you will see some gradation of layers in that particular roasted chicken. So this will be at a temperature which will be higher. Then we will slowly move into much lesser temperature, and then even lesser temperature at the core of the roasted chicken. All right, so let's say here the temperature is almost 180 degree Fahrenheit, obviously. And here, let's say a little lesser than that, 1 degree Celsius also we can tell, that's fine. Here we can take it to be a little lesser than this one, maybe 120. And at the core, let's say the temperature is around 80. So as you can see, when the heating of the roasted chicken starts, so in that case, the temperature not only varies with respect to time, but it's with respect to location also. It's no longer same all throughout the body. So these are the scenarios where we have to deal with a system which is not lumped in nature, and that's why we go for either an infinite solid or a semi-infinite solid. Now, when it comes to infinite solids, remember we are dealing with bodies which are symmetrical about a certain axis. All right, and the primarily three types, like any body in one way or the other, we can model it to be an infinite solid. Like a human body can be modeled as a cylinder, okay, and a furnace wall can be modeled as a slab, and also thermocouple can be thermocouple, or even a sphere can, I mean, like anything which is remotely a little circular in shape can be modeled as a sphere. So all these three things are symmetrical about their central axis. So let's say, sorry, let's say we have a slab which is symmetrical about the central axis. Okay, similarly we can also have a cylinder which will be symmetrical about this is r equals to 0 and this is r equals to r. This is, we call it as x equals to 0, this is x equals to L. So this total length is twice L. Alright, and this is twice R. Similarly for a sphere also, it will be symmetrical about the central axis or any axis in this. So from the center point, this is R, and R goes from 0 to R0 outside radius. And all of them are exposed to an environment which has ambient temperature T infinity and heat transfer coefficient as H. So if these are the scenarios that we are dealing with, then we need to model it as a semi-infinite solid. Now in this case, you see this environment is present all around the body, okay, with respect to wall, with respect to slab, cylinder, or sphere. The environment is present all around it, and that's what gives it the symmetry. So we need to just solve it for half of the uh, portion, and we can just mirror the result for the other half. I'll just illustrate the point with an example. So let's say we have a slab. Okay, the slab is symmetrical about this axis. Let's say the slab is initially, it has been taken out of the furnace, and initially it has a uniform temperature all throughout the body, even at the core as Ti, which is represented as initial temperature. Okay, so the temperature initially I will represent it by this line, and from this end to this end it is Ti. No matter at which location you measure it, it's Ti. All right. And the ambient temperature I will represent it a little down below, and I will represent it as T infinity. Okay. Now as the this side also Ti, as the cooling starts, okay, as the cooling starts, the outside surface will cool before the core starts to cool. Same thing goes with our Earth also. Earth was a huge giant ball of gas, hot gases, and eventually the crust was formed, and the core is still in the molten state. So core will take a lot of time to cool, but not in this case of slab. So initially the cooling will happen. So the temperature profile after some time will look somewhat like this. See, on the outside surface, it has dropped from T1, but the core temperature is still Ti, and the same thing happens on the other side also. All right. After a little bit more time, then we will see that the outside temperature has now almost approaching T infinity, and almost core has started to cool, but still it's at Ti. At the axis, it is still at Ti, and the other side is happening the same. And after some time, after a little bit more time has passed, then we can see that the outside surface has reached T infinity, and the core has started to cool. Now it has dropped from Ti to a certain value. Okay. And if I let it cool for further, then we will see that now the core, almost entire body has come to T infinity temperature. Only core is a little higher than T infinity. And if a little bit more time has passed, then the entire body temperature has reached T infinity. So what you can see, the temperature profile for this half is exactly the mirror image of the other half. So what we can do, we can just solve it for half part and same result can be mirrored for the other. This is a very useful tool even when we are doing a computer analysis. In that case also, we are we will if the object for which we are doing the analysis, if it is symmetrical, then we just take half of that part, do the analysis and mirror the results for the other half. It saves a lot of computational time, and that's why we do it. All right, now when it comes to problems with respect to infinite solid, you can solve it both analytically and graphically. I mean, you have to use your data handbook and certain graphs are there that you need to refer in order to solve the problems. No derivation is there with respect to infinite solids because the derivations are very long and complicated, and also requires a very strong fundamentals of special functions in advanced engineering mathematics. Okay, so what we are going to do next is that we are going to just look into some of the graphs that are available. So in your data handbook, you will find three sets of graphs. Okay, each set will be comprising of three graphs. Each set will have three graphs, and each set will belong to one particular model. Either it will be a slab, or it will be a cylinder, or sphere. Okay, so the first graph essentially, you see, in the x-axis it will be a dimensionless number which is called as the Fourier number. This will be alpha t by L square. This is with respect to slab. Remember that why there is L. If it is with respect to a cylinder, then it will be something related to radius. Okay, and on this side you will have your temperature profile, that is your theta naught. This will be T naught. T naught means your outside temperature, and T infinity. T naught is your center temperature, T infinity T naught minus T infinity, and this will be Ti minus T infinity, and Ti is the initial temperature. So this is your iceless time. So if you can calculate the Fourier number, this is your Fourier number, and this two will be given to you usually. And if somebody asks you to calculate the T naught, you can just use the graph and find out the T naught from that. Okay. Now this is only with respect to core temperature. All right, this graph is with respect to core temperature. Similarly, you can get one more graph. You can get one more graph. Series this one. The second graph, on the y-axis you will have temperature distribution, but not the core temperature distribution. It is the temperature distribution of any location. The T minus T infinity divided by T naught minus T infinity. So if core temperature is known to you, ambient temperature is known to you, you can find the temperature at any location. And on the x-axis, it will be a reciprocal of the Biot number. And the graph looks somewhat like this. There will be different curves. Okay, and each curve is based upon an x by L value. So these are all dimensionless value. So first curve will be x by L equals to, let's say, 0.2, next one will be 0.4, next one will be 0.6, and so on. So if you have a slab, sorry, So suppose you have a slab. Let's say the length is 2 meter. Okay, 2 meter is too high value. Let's say 4 centimeter. 4 centimeter. And if somebody tells you what will be the temperature at a location x equals to 2.1 centimeter, then this is, remember, this is your twice L. So basically your L will, sorry, then this will not be 2.1. Let's say x equals to 0.9 centimeter. Okay, so this is your twice L. Entire length 4 centimeter is essentially twice L. So L is 2 centimeter. So your x by L will be 0.9 divided by 2. So whatever value you get, you just choose the respective curve, or sometimes the value may lie between these two curves. So you just approximately choose a suitable location, and then you can read the temperature distribution, out of which, if you know the T infinity and T naught, you can easily calculate the temperature at that particular location. The last one, the last graph with respect to infinite solid. These graphs will be there for all the three cases. Remember, I'm just showing for the slab case, but these graphs are, all the three graphs will be present for sphere also, and also for cylinders. So last graph is with respect to heat transfer. This is the actual heat transfer. This is the maximum possible heat transfer. Okay, and this is on the y-axis, and in the x-axis it will be again a dimensionless number, but number square into Fourier number. All right, and there will be a set of graphs showing like this, and each one of these graphs is based upon Bayes number. All right, so once you have all the data, you can just calculate, like find out the point where exactly it satisfies your given condition, and then you can read Q naught by Q max, and Q max is maximum possible, so it's just like lump system. Q max will be MCP Ti minus T infinity. If you do that, you can easily calculate Q max, and this is same. It doesn't matter whether it is a sphere or cylinder. M, definitely you have to write it in density into volume, right? You can easily calculate what is the actual heat transfer. Here, this is the actual heat transfer, and this is the maximum possible heat transfer. So if you have this data, then you can easily calculate it. Coming to semi-infinite solids, so what are the situations on which we can apply semi-infinite solid? First of all, the environment will not be available for the entire thing. Like, what I'm trying to say, is that let's say Earth surface is there. So this is Earth surface. All right, and on the top of the Earth surface, let's say there will snowfall will happen. All right, And the snow will stay for, let's say in cold countries, it will stay for around 3 months. This is the duration during which it will stay. So that means the Earth's surface will have, let's say the snow temperature is minus 10 degrees Celsius. So Earth's surface will have a temperature minus 10 degrees Celsius for the next 3 months. So what will happen is that heat, this Earth, the soil will start to lose heat to the snow over the period of 3 months. And the temperature of the depth of the soil, the temperature of the soil will start to drop. Okay. Now in cold countries, when you are supplying water, the water pipes will be laid, underground, because it will freeze during winter season, and as a result the water pipes will burst, so they will be placed underground. But since the snow will be available for 3 months, there is a chance that the soil will start to lose heat, and the depth at which the pipe has been laid will also reach at some point during this 3 months 0 degrees Celsius. So even after reaching a certain depth, or even after laying the pipe underwater, there is a chance that your pipe will freeze during the winter season, and the problem will still be there. So at what depth you need to place your pipe such that even within this 3 month period, the temperature at the level of the soil where the pipe has been laid does not reach to 0 degrees Celsius. So those kind of analysis can require a semi-infinite solid, because you see in case of semi-infinite solid, only the Earth's surface is exposed to this constant temperature. It's not present all around the Earth. Okay, only on the Earth's surface it is present, not all around the Earth. All right, so that is the case. So in that case, we usually use something called as an error function to do that in case of your semi-infinite solid, to solve the problem. Now error function, we can write it like this: at location x, temperature T minus Ti divided by T surface minus Ti is equals to, this is actually error function complement. So you just have to, whatever error function value you get, you have to subtract it from 1, you will get error function complement value. Is 2 into root over alpha T. Okay, so if you know alpha, if you know T is my 3 month here. I know the surface temperature, which is essentially 10 degree minus 10 degrees Celsius. What was the initial temperature? Let's say the initial temperature of the Earth's soil was 30 degrees Celsius. And after a certain time, what is the temperature? Let's say I will do the calculation for 0 degrees Celsius, such that the temperature uh, should be equal to 0 degrees Celsius. And then if I substitute all the value, and this error function value can be obtained from the table that is given in your data handbook. If we do it, then eventually we can calculate the value of x. That means at this level, or at this level, let's say it comes around 5 meter, just for the sake of argument. Then at 5 meter, within 3 months, the temperature will reach 0. So if you are laying the pipe for water, it has to be a value which is higher than 5 meter. All right. So this is one of the scenario where you can use the semi-infinite solid analysis. And also, if there is a sudden change, if there is a very sudden change in the temperature, or much like if you are doing a forging experiment, and all of a sudden you take the heated metal and quench it into water. So those again, only one part of the solid is exposed to a cooling environment. So again, you cannot use an infinite solid. Infinite solid, you have to understand that it has to be present all around your body, which is under analysis. Okay, so in that case, we can go with a semi-infinite solid mode. All right. So let's stop here. Next class, we will start with radiation. And in radiation, we are going to cover some of the basics related to that. And also we will see a special case of problem that usually comes in radiation. Thank you.